Hi, welcome to tutorial 4.2 part 1. This is on reading the solubility chart. So in class we talked about why certain ionic compounds are soluble and why some of them are not. And here all we're trying to do is just keep track of that information. By looking at a chart that's divided up into two parts, it shows some negative ions, anions, that tend to be soluble. They're in the top half of this chart. That's these ions over here. And the bottom half shows the insoluble ions based upon the anions. So the first thing to note, just to kind of get your bearings with this chart, all we're looking at are negative ions. Nitrate, acetate here is written a little bit differently than we did before. It's not written as C2H3O2, but CH3COO-. So that shows a little bit more of the structure. So the chloride, bromide, and iodide ions tend to be soluble, as are sulfates. So most of these are soluble, but there are some exceptions, notably the compounds of silver and lead for these halogens that are ions, halide ions, chloride, bromide, and iodide. And then sulfate has a few other exceptions. Lead is common to these three exceptions, but there's two other ones, strontium and barium. Of the common ions, this doesn't cover every single ionic compound, but it covers most of the ones that we're going to see in the lab. And then on the bottom we have some negative ions, anions, that tend to be insoluble. Sulfides, carbonates, phosphates, and hydroxides pretty much don't dissolve. There are some important exceptions. All the alkali metals are exceptions. So as soon as you see an alkali metal with any ion, you can say, oh, that's going to be soluble. And then there's some other exceptions, calcium, strontium, and barium for both the sulfides and the hydroxides. They're not that soluble, but they're partially soluble, so we're going to say that in general those are soluble. So this chart is it's easy to get confused. These over here, these negative ions, tend to be soluble, but there's some exceptions on the other side. These here tend not to be soluble, but there's some exceptions on the other side. So when you see the exceptions here, we're talking about what is soluble. When you see the exceptions here, we're talking about what's insoluble. That's that. Now let's go ahead and try a few of these. I set the website up. It's a little bit cumbersome. I think I should have put a drop-down menu in, but I just have you actually type in the words soluble and insoluble. So probably what's good to do at the beginning is just type in the word soluble and put it in your clipboard so you have it sitting in there. So I'll just copy that in my clipboard. So when I go to do it, I don't have to type that in every time and waste a lot of time. You've got a couple of minutes at 2 points each. I don't think it should take us too long, but we're going to go nice and slow to make sure we understand it. All right, let's go ahead, hit play. So here we have strontium acetate. So as soon as you see acetate, you say, oh, that's up in the top half, so I bet that thing is soluble. And you check if there are any exceptions. It doesn't say there are any, so that means it's soluble because we didn't find the exceptions. That's the first one. Now you see again. You notice you're ignoring the cation. Just look at the negative anion. Hydroxides. Oh, that's in the bottom half. Chances are that is insoluble. Is manganese nonetheless? The manganese 3 ion part of the exceptions? No, it's not. So therefore, that is going to be insoluble. So I'll type in and paste in my word soluble. All right. How about this one? Carbonates. Oh, that's probably insoluble, because carbonates are down here, but you have to know which ones are the alkali metal ions. Potassium is an alkali metal, so therefore that's going to be soluble. So notice the carbonate mostly is insoluble, but the exceptions are with alkali metals, which includes the potassium ion. All right, hydroxides, we've already seen this one. That's an insoluble one with the manganese. That one is easy. How about sulfides? Yeah, pretty much insoluble, but here it shows an exception with calcium. It's partially soluble, so we're going to go with soluble rather than insoluble. How about acetates? No exceptions there, so that's going to be soluble. Rubidium, I don't have to look because I see whatever it's with, it's an alkaline metal, so that's got to be soluble right away. Cesium's an alkaline metal, soluble right away. Copper is not an alkaline metal, so I have to be careful. Iodides tend to be soluble. They're up at the top half, and I don't see any exceptions here having to do with copper, so it looks like it is going to be soluble. Hydroxides, not soluble, but in the case with potassiums, they are. So again, it's soluble. Rubidium's alkali metal, and the nitrates don't have any exceptions. They're always soluble, so that one's going to be soluble. How about bromides? Soluble? No exceptions with magnesium, so we're with soluble again. I think you get the idea. I don't have to go any further. So you can get lots of points, some extra credit points on this if you want to use this as your quiz. And it's pretty much always the same. I'm going to restate it nice and clear without rushing through the. I do the same as you do. You start rushing when you see that clock going. These negative ions over here almost always are soluble. There's a few exceptions, notably silver and lead ions with these halide ions, chloride, bromide, and iodide. Sulfates tend to be soluble, but again, a few exceptions. Lead was on this list of exceptions up here, and so two new ones, strontium and barium. And then down below, pretty much not soluble, sulfide, carbonate, phosphate, and hydroxide. But you notice in the ones we just did, we mostly were getting these negative ions, these anions, with alkali metals, so they tended to be soluble anyway. But if you didn't have an alkali metal with these guys, or calcium, strontium, and barium for the sulfide and hydroxide, you would say it's insoluble. There you go. That's all there's to it. It's a little bit boring here. However, you'll recognize as we move forward, we're going to need this to write these equations, these double replacement reactions, and these precipitation reactions. So it's going to be an important skill to be able to read this thing both swiftly and accurately. All right, so we'll practice this in class. We'll see you then. Thanks.